previous class I mentioned that we can measure the hydrophobic, hydrophilic nature of surfaces by using an instrument called goniometer, which measures the contact angle of a surface when a water droplet is placed on it. So I thought today I will show you a demonstration of how to use that particular facility that's called goniometer. This is a goniometer, a very simple setup. We can place a drop of water, ultra pure water, on a surface. It could be a polymer surface, it could be a metal surface, and there is a light that's passing, and there is a camera which captures the droplet and the angle the droplet makes, and it comes onto a computer screen, and the computer's software helps you to calculate the angle that the water droplet makes on the surface. So lower the angle of contact, then we call it hydrophilic. Higher the angle, we call the material as hydrophobic. Okay, so when as I mentioned that hydrophilic materials attract less of bacteria, hydrophobic materials attract more of bacteria, and so on. So generally we like to make the surface very hydrophilic. Okay, so let's test it out. I am taking a sample. This is a polyester sample. Polyesters are widely used in medical, especially in vascular grafts and even in some of the diaphragms. So it's biodegradable because it's got a ester bond. Okay, so what we do is we place the sample. Okay, then I turn this knob so that the water comes down and settles down as a single drop. Okay, even from the computer screen you can follow the drop coming down and settling down on the surface. So now I will slowly turn. Okay, can you see the drop there? So the drop comes down. Okay, so you can see the water droplet had made itself settling down with respect to the surface. Now it measures, the software automatically measures both the angles. This is called the receding, this is called the advancing angle. Sometimes the receding angle and the advancing angles could be different, and we will take an average of that. Generally 40-50 degrees angle we can call it hydrophilic, 70-80 hydrophobic. If it's above 100 degrees we will call it super hydrophobic. There are like carbons which are very super hydrophobic. Okay, so it's quite simple. This data can be captured, and then we can do many at different points. We can take an average and so on. Let me try out another sample for you to again view it. Okay, this is another polymer, a PVA. Again I make a water droplet. As you can follow, as I keep turning the knob clockwise, the drop comes down slowly, so you don't have to let the drop fall and splash itself. So again you can see drop makes an angle of around 72-73 degrees with respect to the horizontal. Okay, so this is how we calculate the contact angle, and as I said, lower is the contact angle, higher is the surface energy. The surface is called hydrophilic, higher is the contact angle, lower is the surface energy, and it's called hydrophobic. So attachment of bacteria depends very much on this hydrophilic, hydrophobic. The plasma interaction, that is blood components with the surface, depends upon the hydrophobic, hydrophilic nature of the surface. So this plays a very important role, and as soon as we design a polymer and as soon as we make the surface modified, we have to measure its contact angle. We will continue on analytical tools for determining the properties of various biomaterials which we prepare. We have been talking about microscopes, different types of microscopes, the light microscope, the electron microscope, and atomic force microscope. There are two types of electron microscope. One is called the transmission electron, other is called the scanning electron. Okay. Transmission, as the name implies, the electron beam passes through the sample, whereas in scanning electron microscope it is reflected back. Atomic force microscope is not really a microscope in the sense of light and electron. Here a cantilever moves and the movement of the cantilever, the up and down movement of the cantilever because of the indentation or the roughness of the surface is captured. So basically in atomic force microscope the roughness of the surface is captured, and that is represented in a pictorial form. So all these microscopes are very important, we use quite a lot in biology. The light microscope is used to look at biofilms. If you want to go deeper and look at the bacterial attachment, we can go into scanning electron microscope. If you want to look at nanoparticles, if you want to look at drug delivery system, we use transmission electron microscope or atomic force microscope, because these are having a higher resolution. We can go even up to 1 nanometer. The scanning electron, I would say about 20, 30 nanometers, maybe 100 nanometers. Okay. So for example, if you look at this picture, this tells you the surface roughness. This is a polymeric material. It gets rough when it is incubated for a very long time in body fluids. So this is a scanning electron picture of this roughness, and the same thing is shown through AFM. So we can get better resolution with the atomic force microscope. So it is very important to know whether the surface gets roughness, what is the scale of roughness when the surface gets affected, and so on. So these are quite powerful tools. Now let us go to the next analytical tool, like X-ray powder diffraction, X-ray powder diffraction technique. This is used for phase identification of a crystalline material. So when a material is in crystal form, for example, if you look at metals, if you look at some polymers which are in crystal form, inorganic material in crystal form, then this is very useful. Okay. We can look at whether material is in crystalline or whether it loses crystallinity because it stays inside the body, because crystallinity has a lot of effect on other properties like the melting, maybe the degradation and so on. For example, amorphous material degrade faster when compared to crystalline material. So crystallinity has a very important bearing, number one. Number two, when you are adding some other metals into existing crystalline system, the crystallinity changes. So we can monitor that sort of factors. We can also get the dimensions of the crystal, that is called unit cell dimension. So all these could be obtained from X-ray powder diffraction, which is quite a important bulk property. So the interaction of the incident rays with the sample produces an interference which is observed, that is the diffracted ray is observed and the various crystalline phases are seen in that diffracted ray. If you remember in your school day physics, you would have studied something called Bragg's law, right? Bragg's law. So we have an incident ray which has got a wavelength of lambda, okay, n could be 1 here, d is the dimension of the crystal, theta is the diffracted. Okay. So we use this formula, from there we can calculate d. So for example, this is a typical X-ray diffraction picture. This is a commercial hydroxyapatite. So we can see some sharp peaks here, right, which is characteristic of hydroxyapatite. So we can go to literature and then find out whether these values are matching. So we can say I have a hydroxyapatite, and the x axis generally you plot 2 theta, that is here, right, 2 theta here you plot here, and then from this using this formula from the theta value we can calculate the dimensions of the crystal. So the crystal size is 28 nanometers, crystal volume is 534 nanometer cube, and the crystal cell has got a 9.45 C is 6.91 nanometers. So any crystal is a 3 dimensional, you will have a B, C as the 3 dimensions, alpha, beta, gamma as its angles. Okay. So from this 2 theta value we go to literature and see whether it matches exactly with hydroxyapatite. So we can tell whether we have really prepared hydroxyapatite, and if I am going to do modifications, these 2 theta values can get shifted or the crystallinity will be lost. So, we make a lot of conclusions based on that. Okay. So, X-ray is very useful, we call it powder diffraction because we take a powder. X-ray is nowadays used quite a lot for protein structure determination. Okay. So, let us call it diffractometer, X-ray diffractometer. If you want to know the protein structure, the locations of various the atoms. Okay. So, it is a very powerful tool. X-ray diffractometer is used to determine the protein structure. There is a protein data bank PDB, and if you go into that you can see the 3-dimensional structure of a large number of proteins. So, crystallizing proteins and then looking at their 3-dimensional structure, again we use X-ray diffractometer. Okay. Now, let us look at another technique, it is called TGA, thermogravimetric analyzer or thermogravimetric analysis. So, it is a method of thermal analysis in which change in physical chemical properties of materials are measured as a function of temperature. So, this look at this picture. Okay. So, we increase the temperature and then we monitor the weight loss. Okay. So, from there we make a lot of sense at which temperature the initiation of the weight loss starts and how much is the weight loss and what is the final ash left behind, that means it is not completely removed. So, some ash is left behind. So, TGA we call it is a very useful technique, especially we use quite a lot in polymeric system because the place where the temperature at which the weight loss started becoming maximum, it is a useful value to have. Sometimes some polymers may have 2 temperatures at which weight loss may happen. Okay. Initially there could be loss of some hydroxyl groups which are easily removable, and there could be another temperature, higher temperature, where it could be more difficult for it to lose its weight. So, we can detect chemisorptions, dissolvations, decomposition, solid gas reaction. So, basically what does it do? It continuously weighs a sample as it is heated. Okay. So, we can go up to 500, 600, even 800. As the temperature increases, various components of the sample are decomposed. Okay. So, the material loses its weight, so it comes down. So, for example, in this picture if you see one material you loses a lot of weight, another material you loses only little weight. Okay. So, we make a lot of sense, and also when you take a differential d weight by d temperature, okay, and if you plot that you can see here. Okay. So, this red one, for example, this particular material is losing especially at this temperature, whereas this material is losing at this particular temperature. Okay. So, that it may be difficult to look from this graph, but if you take a differential dW by dt and plot temperature, it gives you a very nice picture of where the materials are, at what temperature each of these materials are losing their weight. So, it is a very powerful technique to understand what type of materials are there. For example, if you take a blended polymer, one polymer may lose weight at one particular temperature, another may lose weight at another temperature. So, depending upon the composition of the 2 polymers, you may get a thermogram like this, it may fall and then after some time another fall can happen. Okay. So, this is a very useful technique to understand the phase change of materials, especially in the area of polymers. Okay. And then we can also know if there is a coating which is easily evaporated. So, as soon as the temperature is increased, whatever coating will get removed, so there will be a weight loss, we can see that. Okay. So, we can identify what is the stability of the material, especially if you are going to do a sterilization of the biomaterial, if you are going to do a steam sterilization. So, steam sterilization we say about 100 degrees or 110 degrees. So, the coating or other material should not start going out of the polymer. Okay. So, those things can be easily determined or identified when we run a TGA. Okay. So, TGA is quite useful in that. Then similar to TGA, we also have something called differential scanning calorimeter or calorimetry. So, what it does is it measures the difference in the amount of heat required to increase the temperature of a sample. Okay. So, here you plot heat flow versus temperature, whereas in TGA we plot weight loss versus temperature. Okay. So, DSC heat flow versus temperature. So, if I am converting a material from say solid to liquid, I need to put in heat. Okay. So, the heat flow will be positive. So, if I am converting from liquid to solid, so it will be reverse. So, it will heat flow will be negative. So, we can detect the phase transition. So, there is a measurement with respect to the reference. Okay. So, you are measuring the heat input or heat coming out, that is heat flow in or heat flow out with respect to a reference. So, we can detect phase transition. So, we can look at exothermic or endothermic type. So, whether the heat is given out by the material or heat is taken up by the material. So, we can measure something called glass transitions, that is it's especially polymers exhibit this type of behavior, glass transitions. This is a reversible transition in amorphous material from a hard relatively brittle state into a viscous or rubbery state as the temperature is increased. Okay. Tm is the melting temperature, Tg is called the glass transition temperature. Okay. Tg is always less than Tm. Tm is the melting temperature, that could be very high, 300, 400 degrees, whereas glass transition can happen at 30, 40, 50 degrees. Okay. So, so at this temperature there is a phase change, okay, from a hard and relatively brittle state into a viscous or rubbery state. Okay. That is called glass transition. So, some materials can have even 30 degrees glass transition. So, when we are talking about body temperature, we have to be very careful, okay, because it will be changing its phase, that is called glass transition, and that will be much smaller than melting temperature, that is Tm. Melting temperature, as I said, for example, can happen at 300 or 400. So, you have to put in lot of heat for melting, okay, as this graph shows. Okay. Whereas glass transition could be around 30 or it could be 20 or it could be 100 up to in that range. So, material is becoming from hard to more of a viscous or rubbery state. Okay. So, two different thermal techniques, one is called the TGA thermogravimetric, so weight loss as a function of temperature, another one is the heat input or output as a function of temperature. So, when we do this on polymers or polymer blends, we understand quite a lot of details, how stable the material is with respect to changing heat, do they change their phases as well, what is the glass transition temperature of the material, all those details we can try to identify using these type of techniques. Okay. Okay. Then we have a lot of spectroscopies used in biology. So, spectroscopy measures the interaction of the molecules with the electromagnetic radiation. Okay. The spectroscopies could be atomic absorption spectroscopy, atomic emission spectroscopy, ultraviolet visible, that is UV visible spectroscopy, infrared spectroscopy, Raman spectroscopy, nuclear magnetic resonance or NMR, then photo emission spectroscopy, Morse-Bayes spectroscopy. Okay. So, if you look in the area of biology, biomaterials, we use quite a lot of this UV visible and IR. IR is used to look at the functional groups, UV visible is used quite a lot in biomolecules. Spectroscopy is like NMR, mostly used by synthetic organic chemists to identify, characterize the product which they are producing. Atomic absorption, we can use it to determine elements, the various elements, metallic elements present in a material. Okay. We can use, for example, yesterday I talked about EDX, okay, energy dispersive X-ray, which also can be used to determine elements, but mostly EDX operates on the looks at only surface, whereas A can be a bulk, and we can find out what are the various elements present in the material. Okay. So, we will talk more about these two actually, we will not spend much time on remaining. Infrared IR or FTIR, Fourier transform infrared, is a very powerful and useful tool which we will be looking at quite a lot in biomaterial area. Okay, so if you look at electromagnetic spectroscopy, there is an interaction of matter with the electromagnetic radiation. Electron spectroscopy, interaction with electron beams. Auger spectroscopy, it is inducing Auger effect with an electron beam. So, the measurement are looking at kinetic energy of the electrons. Mass spectrometry involves interaction of charged particles with magnetic and electric fields. We are going to look at this more in detail, because if you are making a material like an inorganic, or if you are making a organic polymer, I need to know what is the mass. So, mass spectrometry is very, very important. Acoustic spectroscopy, mostly solid material, involves the frequency of sound. We can look at cracks, especially in aeronautics engineering, they use quite a lot of this. Dielectric spectroscopy involves frequency of an external electric field. Mechanical spectroscopy involves frequency of an external mechanical stress. Okay, so later on I am going to talk more on mass spectrometry. Electron spectroscopy is more like a scanning electron and so on actually. Okay, so some of them we will not bother, some of them we will talk a little bit in more detail, because they are all involved in the area of biomaterials. Okay. So, as I said, again we will spend more time on infrared spectroscopy, because we can look at the functional groups that are present on a surface, and if I do some modifications, what is happening to those functional groups, and as a function of time, if there is an oxidation of your material, we can find out those things using an infrared spectroscopy. Okay. Then we have the fluorescent spectroscopy, which uses higher energy photons to excite a sample. So, when you energize a sample, it will emit lower energy photons. So, that lower energy photons is characteristics of the sample. Then we have the absorption spectroscopy. So, there is a power of beam of light measured before and after interaction with the sample. So, we compare how much of the material is absorbed. Then of course, the infrared spectroscopy. So, it measures different types of interatomic vibration. So, you could have vibrations of the bonds between two atoms, or there could be a bending and there could be a torsion. So, the different frequencies, based on the frequencies we can tell what type of bonds that are present. Okay. So, all these spectroscopies are used, as I said, in biomaterial, they are used in chemical analysis, they are used in organic chemistry, they are used quite a lot in inorganic chemistry as well. Okay. So, we will talk a little bit in more detail on some of these techniques. Okay. Thank you very much for your time.